Hello, everyone. Today we are going to dive into the foundational concepts of fluid mechanics. By the end of this video, you will be able to describe how fluids move and interact with surfaces, calculate key properties like viscosity and the Reynolds number, and distinguish between different types of fluid flows. We have a lot to cover, starting from the basic velocity field and moving all the way to complex flow classifications, like laminar and turbulent regimes. Our first objectives are 1. Define the velocity field, and 2. Distinguish between 1D, 2D, and 3D flows. The velocity field describes the velocity of fluid particles at any point in space and time. To understand how a fluid moves, we define the velocity field. This field describes the velocity of a fluid particle at any specific point in space and at any given time. Mathematically, the velocity vector v is composed of three components, u, v, and w, which correspond to the x, y, and z directions respectively. In a one-dimensional flow, the fluid parameters vary in only one space dimension. An example is flow in a long straight pipe, where we assume the velocity only changes along the length. Two-dimensional flow occurs when the velocity depends on two coordinates, such as flow over a very wide weir or a long cylinder. Three-dimensional flow is the most general case, where velocity varies in all directions, like the air moving around a complex shape like a car. Consider a 2D velocity field, where u equals 2 times and v equals 3y. At the point 1, 2, the velocity components are 2 and 6. The speed, or magnitude, at that point is the square root of 2 squared plus 6 squared, which is approximately 6.32 units. Try this. If v equals 4t in the I direction and 2 times in the j direction, what is the velocity at x equals 1 and t equals 2? The answer is 8I plus 2j. Next, we need to visualize how fluids move over time. We use 4 distinct types of lines to describe flow patterns. Our objective is to distinguish between streamlines, path lines, streak lines, and timelines. First, streamlines. These are lines that are everywhere tangent to the velocity vector at a given instant. They give us a snapshot of the flow direction. The governing equation for a streamline in 2 dimensions is dy over dx equals v over u. Second, path lines. A path line is the actual trajectory traveled by an individual fluid particle over a period of time. Think of it like a long exposure photograph of a glowing buoy in the ocean. Third, streak lines. This is the line formed by all fluid particles that have passed through a specific fixed point. Imagine injecting smoke at a single point in a wind tunnel. The smoke trail is a streak line. Finally, timelines. These are formed by a set of adjacent fluid particles marked at the same instant in time. Note that in steady flow, where the velocity doesn't change with time, streamlines, path lines, and streak lines are all identical. They only differ in unsteady flow. Think of a rotating sprinkler. The water droplets flying out follow a straight path line, but the continuous spiral shape of the water stream you see is the streak line. Quick check. If the flow is steady, are path lines and streamlines the same? The answer is yes. For steady flow, all 3 lines coincide. Now let's talk about the forces acting within a fluid, specifically the stress field and viscosity. In a fluid, forces are expressed as stress, which is force per unit area. We have normal stress acting perpendicular to a surface, and shear stress acting parallel to it. Viscosity is a measure of a fluid's resistance to deformation or thickness. Dynamic viscosity, denoted by the Greek letter mu, relates shear stress to the rate of deformation. Kinematic viscosity, denoted by nu, is the ratio of dynamic viscosity to the fluid density, rho. In a Newtonian fluid, like water or air, the shear stress is linearly proportional to the velocity gradient. Non-Newtonian fluids, like ketchup or blood, do not follow this linear relationship. Their thickness changes as you apply more force. A viscous flow is one where friction effects are significant. An inviscid, or non-viscous flow, is a theoretical model where we assume viscosity is 0 to simplify calculations. Notice this velocity profile. Due to viscosity, fluid sticks to the solid wall. This is called the no-slip condition. Compare water to honey. Honey has a much higher dynamic viscosity, meaning it requires much more shear stress to flow at the same rate. Try this. If a fluid has a density of 1,000 kilograms per cubic meter and a dynamic viscosity of 0.001 Pascal seconds, what is its kinematic viscosity? The answer is 10 to the power of -6 square meters per second. Another fascinating property of fluids is surface tension, which allows insects to walk on water. Surface tension, denoted by the Greek letter sigma, is the intensity of the molecular attraction per unit length along any line in the surface. It acts like a stretched elastic membrane. For a curved surface, like a spherical droplet, the internal pressure is higher than the external pressure. This pressure difference, delta P, is equal to 2 times the surface tension divided by the radius r of the droplet. In many engineering approximations, we refer to an ideal fluid. An ideal fluid is defined as being both non-viscous or inviscid and incompressible. While no real fluid is truly ideal, this model simplifies many complex problems in aerodynamics and hydraulics. As seen in this diagram, surface tension tries to pull the droplet into a sphere because that shape has the minimum surface area for a given volume. Let's calculate the pressure difference for a tiny water droplet. If the radius is 1 millimeter and the surface tension of water is 0.072 newtons per meter, the pressure inside the droplet is 144 pascals higher than the outside air. Think about this. If the radius of a bubble doubles while the surface tension remains the same, what happens to the pressure difference? Since the radius is in the denominator, the pressure difference is halved. Now, let's look at one of the most important ways to categorize fluid motion: laminar and turbulent flow. Our objective is to calculate the Reynolds number and distinguish flow regimes. In laminar flow, fluid particles move smoothly in layers, or laminae, that slide over one another. There is no mixing between layers. Think of a steady stream of honey. Turbulent flow is characterized by chaotic motion and eddies. This causes rapid mixing of the fluid. Think of a rushing whitewater river. To predict which type of flow will occur, we use a dimensionless number called the Reynolds number, abbreviated capital R, small e. It is the ratio of inertial forces to viscous forces. Here, rho is density, v is velocity, L is a characteristic length like pipe diameter, and mu is dynamic viscosity. For flow in a pipe, the transition from laminar to turbulent usually happens around a Reynolds number of 2,300. In this visual, you can see how the velocity profile for turbulent flow is much flatter than the parabolic shape of laminar flow due to the intense mixing. Let's calculate the Reynolds number for water flowing at 0.1 meters per second in a 5-centimeter pipe. Since 5,000 is greater than 2,300, this flow is turbulent. Take a moment. If the fluid becomes more viscous, does the Reynolds number increase or decrease? The Reynolds number decreases, making the flow more stable and likely to be laminar. To wrap up our flow classifications, we must distinguish between compressible and incompressible flows, as well as internal and external flows. A flow is considered incompressible if the density of the fluid remains nearly constant throughout the flow. Most liquids, like water, are treated as incompressible. In compressible flow, the density changes significantly. This is common in high-speed gas flows, such as air moving around a supersonic jet. We often use the Mach number to determine if compressibility is important. If the Mach number is less than 0.3, even gases can often be treated as incompressible. Internal flow occurs when the fluid is completely bounded by solid surfaces, such as flow through a pipe or a duct. Here, the development of the boundary layer is limited by the walls. External flow occurs when the fluid flows over an unconfined object, like air moving over an airplane wing or water flowing around a submarine. In the pipe on the left, the fluid fills the entire volume. On the right, the airfoil is surrounded by an infinite or very large expanse of fluid. Let's check the compressibility. The Mach number is 100 divided by 340, which is approximately 0.29. Since this is less than 0.3, we can simplify our analysis by assuming the air is incompressible. Think about this. Is the water inside your garden hose an example of internal or external flow? It is an internal flow. The fluid is bounded by the hose walls. We have reached the end of our journey through fluid fundamentals. We've covered everything from velocity fields and visualization lines to viscosity, surface tension, and complex flow regimes. You now have the tools to describe and categorize almost any fluid situation you'll encounter in engineering. Keep practicing these concepts.